approaches 0 from the difference quotient. And then in chapter 3, we talked about differentiation rules to shorten all this process. Same thing here now in chapter 5. We are talking about the limit of the Riemann sum because we want to understand how we get to the shortcut. And I will get to that in a minute. But the question is, why? Why am I calculating the area under the graph of a function? And now I would like to share my screen. And I like to look at something like this at first. We are given a table. I don't like the fact that they are talking about the integral. I don't want to talk about this symbol yet. We are not ready. I just want to understand at this point why we're doing what we're doing. So disregard this, okay? So this problem is asking us, they are giving us, the table gives the values of a function obtained from an experiment. Fine. Use them to estimate the area under the graph using 3 equal subintervals. And they're given us, we don't have to do all of it, the right end point, the left end point, and the midpoint. We can just choose one. So that's one possibility. The second possibility that I would like to look at is a function. I couldn't find in the book a function that gives, so they're all jumping into the symbol, but we don't know what the symbol is yet all about. So right here, I think this is a better starting point. It says use 6 rectangles to find estimates for each type of the area under the graph. Okay, so here's the graph of a function. Let's assume that this is the velocity. I'm assuming that this is the velocity function. And I'm asking you, let's find the distance covered by the particle between time equals 0 and time equals 12 seconds, minutes, hours, whatever you want. In order to determine that distance, all I need to find is the area under the graph. Finding the area under the graph of the velocity function, it will give us the distance covered by the particle or vehicle between 0 and 12. So this is why we calculate. Okay, got it. The velocity graph of a car accelerating from rest to a speed of 120 kilometers an hour over a period of 30 seconds is shown. So this is the velocity function between 0 and 30 seconds. Estimate the distance traveled during this period. It's nothing else but an estimate of all these rectangles under the graph. So we are reversing the process of differentiation, because that's the velocity, in order to determine the distance. So if I can use any method, let's suppose they're not telling us how many rectangles. A rough estimate will be, let's say I want base times height plus base times height and plus base times height. That will be a rough estimate. And I'm going to look at the graph and just write down. So the area, which is the distance between 0 and 30, will be base, which is 10. I'm going to estimate times 80 plus another 10 times, I'm going to estimate this height, as being 110, because this is 100, so 80, 90, 100, 110, and the last one is 120 plus 10 times 120. So this is the distance covered by the particle. We were given the velocity function between 0 and 30. So I split it into 3 subintervals. Is this an accurate estimate? No, it's not. First of all, it will give me an overestimate for sure because of these pieces. But this is a rough estimate, and I will tell you, not more than, 800 plus 110 with a 0 plus 120 with 2 zeros. So 3100, and the measurement unit was, I'm going to share again, the measurement unit was in kilometers. That's the reason why we look at the area on the graphs. So the area that we just determined is a rough estimate of the distance traveled during this period. Any questions? Any questions on this? Anyone? And we can look at other situations if you'd like. This is just showing what it represents. So basically, this is just decomposing the limit. Of course, it's a limit. When that's an error, sorry about that, it's not x approaches infinity, it's the number of subintervals n approaches infinity. Okay, so here these 3 have x, it should say n. There is no x anywhere, so it makes no sense. It's the number of subintervals. So the limit as n approaches infinity, obviously this must be delta x, and this must be xi, and the function must be x to the 3rd. There's no discussion there. So determine a region whose area is equal to the given. Of course, we cannot evaluate this limit. We don't know how to evaluate this limit. So they are just asking us, okay, can you tell us what this means? What is the function and what is the region over what interval? So that's what this means. Let me know if you want to work on any of this. Again, here they are giving us, so this is, we can do that. I think that this would be a good practice. Although we are not equipped to determine any of these. Do not evaluate the limit. They don't have to tell us. Even if we wanted to, we couldn't. Okay. So let's look at, let's say 18. So f of x equals x plus natural log x. The interval is between 0 and pi. So they're just asking us to find an expression. Find an expression for the area under the graph. So let's do that. So obviously our preps, delta x, pi minus 0 over n. So this is pi over n. Second prep is the xi. Can anyone tell us what xi equals to? Anyone? 0. I don't have to write it. Plus I delta x. So this is pi I over n. And prep number 3 is f of xi, which is pi I over n plus natural log pi I over n. So finally the area equals the limit as n approaches infinity from the sum from I equals 1 through n. From delta x, pi over n, multiplied by all this. Base times height. So pi I over n plus natural log pi I over n. We cannot determine any of this. That's all they wanted us, to come up with an area. With an expression for the area, I should say, not with the area. Any questions? Any questions?
Yes.
Yes, please.
We go back to the problem that we did before.
Yes.
So in that one, it was a function of a speed, and we calculate the area underneath. It gave us the distance.
Yes.
So from previous classes, we learned that the derivative of distance will give you the velocity. So is that what we always calculate for the area underneath of the function, the previous derivative answer?
So I do not have the function s of t. If I had s of t, I wouldn't have to determine the area. I don't have s of t. I do have, if I had v of t, I would have determined s of t, but I don't have v of t. I only have a graph. So I'm asked to estimate, based on the graph, which is the graph of the velocity between 0 and 30, I'm asked to estimate the distance covered by the vehicle. So I'm asked basically to determine this area. Otherwise, I would have determined the distance using anti-differentiation. But since I don't have this, I cannot have this. Was that the question, Oscar?
Yeah. So in that way, whenever they ask us a problem, like I can picture example what they're asking. Yes.
Okay, so this was a graph one more time. The velocity was not given. I was just told that this is point by point graphed, and we don't have a function. Still, I can still estimate to determine by determining the area under the graph. It was an estimate because it was an overestimate, obviously. But this is the process that I'm trying to get to. It's called integration. I just didn't want to use the word just yet. So the reason why we find areas under graphs, so when I want to determine the area under a graph, so the graph is right here, so I want to determine this area, I'm really determining I'm evaluating the function that is the antiderivative at 7 minus the antiderivative at 1. But I cannot get to that before I talk about the integral symbol yet. And I will come back to this problem, and we will determine it by hand to check this answer. I promise you I'll go back. So that was the next step that I wanted to accomplish. So there is another way other than A, the exact area limit, as n approaches infinity from the sum from I equals 1 through n from delta x f of xi, which is the exact area under the graph. There exists another way of determining this. Like I mentioned a few minutes ago, we used, where are my notes here? So we used this initially, and then we looked at the shortcut, and now we looked at the limit of the Riemann sum, and now we're going to look at the shortcut. And what is the shortcut? So remember we used the Greek letter S, which is the sigma notation. This time we are going to use the Roman S, if you want, but a stretched S. So instead of writing this, I'm going to write this. It's the same thing. It's still talking about a sum. It's still talking about a sum of the product, or sum of products, base times height. base times height of areas. Still the same thing. So we're talking about the interval a comma b. So this area, the limit of the Riemann sum, will be exactly the same with the area, with the definite integral. Definite integral from a to b from the same thing. F of x dx. Remember, we talked about dx and delta x. They are the same. In the limit of the Riemann sum, we use delta x. In the integral, the definite. Why is it called definite? Definite because it has a lower limit and an upper limit of integration. So a is the lower limit, and b is the upper limit.
I have a question.
Please, anything.
Can you go up a bit where the numbers are? How'd you get the number 3?
So, let me go back to a simpler example. So after we determined xi, we simply plugged it in. 2 in parentheses 1 plus 6i over n cubed plus 4 in parentheses 1 plus 6i over n minus 3. So once I determined xi, to find f of xi, I plug in pi I over n in the function. So x is pi I over n, and x is pi I over n.
So do they give you the change in x?
The delta x?
Yes. Is it given? Or
It cannot be given. We are dividing by n subintervals. So we have n subintervals. I cannot determine this, n, because n will go to infinity. If I am told approximate the area under the graph between 1 and 7 with 4 subintervals, then yes, I have 6 over 4. But I'm asked to find the exact area, and I have n subintervals. From the first subinterval to the last one, n, right here. I don't know how many they are, and I don't care, because n will go to infinity. From the first subinterval till the last subinterval, but the limit is when n approaches infinity. So that's why we don't have n. Is that better? Yeah, n is not given to us. So think here, maybe it's not clear. So n is the number of subintervals. And n will eventually approach infinity. Is that better now?
yes, it's better.
Okay, perfect. So now we know that this is the difficult part, and this is restricted. We can only determine this for linear, quadratic, and cubic. If you ask me to put something like this, I have no idea how to calculate this, because we only have those identities for these 3 functions. But this is a different story. Let's talk about the definite integral now. What is the definite? How do we determine the definite integral? So the integral from a to b, from f of x dx, is calculated, is determined exactly by finding the antiderivative of this function, the function whose derivative is f of x, and then evaluated from a to b, which really means I plug in b and I subtract when I plug in a. I don't want to forget to write f of x must be continuous. This has a name. Fundamental theorem of calculus. And this book is considered part 2. In other books, you're going to find it as part 1. It doesn't matter. I'm going to show you both parts. So coming back to our first example from last time, when we had that function from 0 to 2, we had that simple function dx. And I put it in, I recycled it. Let me take it out. Here it is. And we found it exactly as 8/3 using the limit of the Riemann sum. And let's see what we get now. Can anyone give us the antiderivative of x squared?
X is a third over 3.
Excellent.